Good morning, everyone. Sorry I'm late. I lost track of the link. Can everyone hear me okay? Anybody? Okay. I don't yet know if anyone can hear me. So I'll open the chat. I can hear someone. Okay, great. Thank you. Awesome. And now I'm co-host. Okay. I am excited to do this for y'all. The preparation.
Welcome, Dad.
Well, hey.
You are a co-host now. You can share your screen and you can do everything. Right.
Excellent. I will share my screen here. There we go. I really wish that I can only see. So you'll have to help me. The Zoom on Linux works well, but it has some drawbacks. So one of them is I can't see everyone's faces. So I'll do my best here. I will, by the way, Guy had to cancel class today, so we can run over today with questions, which will be nice. And I will run through what we did last time very briefly. I hope you enjoyed the time with Guy. So here is our fake feature creation. This is very powerful, as I explained last time, because we don't have to go hunting for data just to learn how to use the tools and the processes and the set of methodologies to do good machine learning. We can always create features somewhat like this. Now, notice I've done very well scaled data from 0 to 1, and I created 1,000 points of each. And I'm hoping y'all remember that in case there's someone new here, you get the benefit of seeing at least a quick review. Then we use this NumPy technique to column stack, horizontally stack these vectors together. And that's why I did this reshape to turn them into column vectors. And this is a trick that lets you take the one dimension it knows about and use it first. Then we created our fake labels, but we also even created some fake noise. We took the max value of this model. So we've got 1.0 times x1, 2.0 times x2, etc. And then we used a noise level of 0.07. Now, since I'm going to do random normal noise, I used 0 for my mean and 0.07 again for my standard deviation, same value as the noise. And then I go, I use this peak noise times peak noise. So that's to get that standard deviation level. And that means it's actually going to go a little more than one standard deviation out. Then 1 plus equal y noise. This is a fast way to just add this uniform distribution of noise back to this. And you can see how it went from only -4 to +4. Reconcile that for yourself. And I'm trying to write my workbook cells so that they're more independent of stuff above. Now, as we discussed too, we need a training set and a test set. And oh, thank you, Hugo. Hugo, do interrupt me if you need to call my attention to a specific question. So now we're just checking that we created the train and test sets that we expected to with this tool from scikit-learn's model selection suite. And we used and I just renamed this the scikit-learn model selection. But in that, we did the train test split class and instantiated this and got, and it may be just a function, but it gave us all these values this way. Now we went through, let's see, did I run that? No. And then I'll skip through some of this because you can look at it on your own later. But I explain how we do model selection and that we're starting with very clean data. And here I'm just loading a suite of metrics tools that you can study on your own later, scikit-learn metrics. And I create this function that will run all these metrics for me each time based on y-test and our predicted y's and the number of model parameters we used. Hang on 1 minute while I clear my throat. Thank you. And then we ran through all these model algorithms, but we saw, with the exception of hyperparameters we need to set, that they all have this similar format. In fact, to make it simpler, we could have instantiated all of them to the name mod, but I did this just so we could distinguish them. So this is the model for linear regression, and we always see the same pattern. We instantiate the class, then we fit with our training data, and then we check the score. And if there's coefficients, we look at those, and you can see it came very close to the coefficients we created the fake data with. That's why we're doing this, because if we weren't creating our own data from our own model, we wouldn't know how well we were doing. So this gives us an extra insight, almost data profits, when we do it this way. So we do that training, and randomly it's going to change each time, right? And then each time you run new features above, it's set at this level. And then we see that it did a really good job when we look at the R squared and the R squared adjusted. And so that's after we did the predict with the test X data. And then we compare the Y test to the Y predicted to get these metrics. That's what's going on. And we did that over and over for all these methods. And then finally, I'll jump down to crossfold. This is a very important class, or method, we should say, if we're not going to be too tool-centric. We imported cross-validate from the model selection class. And for the model in these lists, we did each of these models that we tried above, and we ran a cross-validation on each of them. Now, what's cross-validation? It gives every piece portion, so in this case, 5 portions in the data set, the chance to be the test data, whereas the other 4 portions, or 80%, are getting a chance to be the training data. And then we're looking at here, you can see, what did I choose to do? I looked at the scores, but I called the train score and the test score to compare them. And we can see that the accuracies, and we've got pretty clean data here, of course, they're flat. They're high and they're flat. And that's what we want. We don't just want the highest accuracy model for any one fold. We want a model that gets good accuracy across all the folds, because that means when new data comes in, it's more likely to get good results on new data. So it's very important the way we train and test our models. Okay, well, like I said, we started with really good data. So how to get good data like the above data? Let's go in reverse order to see how we get to good data for modeling from real world data. Now, keep in mind, we're going backwards. We're saying, oh, it'd be great if we could always get models that were that accurate. So what are the techniques we do to get the data in the best shape possible so that we can do that? Okay, so first thing, in backwards order, sometimes we need to engineer new features. I'm stopping in for a minute. Hugo, do you want me to address anything?
Okay, there's a question on the chat. Karim is asking if there is another library apart from scikit-learn with all these tools, metrics, and all that. And probably why they seem to prefer scikit-learn to every other
Very good
ones.
question. Kareem, I'm going to ask you to ask that question during the Q&A so that we don't get off track right now, but that is a good question I'd like to cover. And yes, all these links will be shared like Hugo said. Hugo, remember, I'm here to teach, you're here to lead, okay? So if it's okay, I'll move on.
All right, that's fine.
Okay, good. Now, notice I'm creating some more uniform fake data, but just one feature, a unit, we call it a univariate feature. And I'm going from 0 to 2 for this number of points again, 1,000. And I do that reshape again. And then I have a simple model. It's 2.0 times x squared. Now, this is the cool thing about NumPy. I just created this array of 1,000 points. And when Python knows it's a NumPy array, what this means is it's going to square every value in that array. Then I create a higher noise percent. And then I look for that peak noise again. And then I do random normal noise and I add it back into Y. And then, so let's run these real quick so you can see that I didn't just doctor all this. And then we'll see that we create that noisy curved data again based on the model. Now we don't have a model for this yet. This is a scatter plot. Let's do a little trick real quick together so that that's easier to see. Plot. Now, again, plot is just an alias for matplotlib.pyplot, so we don't have to type that every time. And I'm going to access the figure, and I'm going to set the fig size to something bigger. Now I'm going to make it kind of strangely large. So I'm going to go to 8 by 16. Oh, I should be doing that in a tuple. Another little trick. I'm going to just try to be very verbose today. Notice how I highlighted all that. Now I'm hitting the left parenthesis. Boom. Saves time. Kuyen would be proud. Okay, now when I do this, I get a bigger plot. And I will never confess. Was it on purpose or was it by accident? It really doesn't matter. It's going to happen both ways many times throughout this class. So now it's a little easier to see these 1,000 points scattered. So remember, this is a great trick to improve your visualizations on simple matplotlib type plots. Okay, now we use that same trick. I want to create training data and test data. So I run this. And please don't be shy if I'm going too fast. I'm doing it so that we get to take the next hour too, if we want it, because Guy had to cancel class. But I tried to make this bite-sized so it was an initial introduction. Now we instantiate that learning class again. And oh my, we didn't get the high score that we had been getting. And look, we knew there should be a coefficient of 2, but there's not. Let's get a visualization clue about that. Let's run our metrics. That's a form of visualization. Oh, wow. Yeah, the R squared, it's low. Okay. Well, let's see what's going on there. Pretend you hadn't seen that yet. And let's go on ahead and get our little trick up here again. I'll put it in my keyboard buffer. So that we can use it later as we need it. And so I'm just going to put that there so we can see this a little better. And now we see the problem with the we tested it with the test data, and well, this wasn't linear. We need linear relations for linear regression. Is that a problem? No, not at all. We just need to square our training data. Now, We know this as data, fake data profits. But what if we didn't know? Well, we could, if it was just this simple univariate problem, this would have been a good clue that we needed something with a power on the features, or we needed a log of some kind, or a square root on the label. We could go either way. But I'm gonna rerun this again. Again, we're pretending we're guessing. We know because we created the fake data. But let's run it. Oh, wow, the score is up close to 1 again, essentially 1. And then we do the prediction and we do the metrics again, predict, and then do the metrics with the prediction. And look, we're up there again. And I still have that in my keyboard buffer, so we'll add it. And let's look at a nice big plot of this. Oh, nice, that's what we want to see. But why does it look linear now? Because we knew that the label was based on x squared. So I'm actually plotting x squared versus y. And we should expect it to be linear now. And if that's confusing to you, anything, let me back up a minute and be pedagogical and philosophical with you. Pedagogy is just a fancy word, guys, for teaching or teaching philosophies. But let's put more of an emphasis on your learning and less on my teaching. How do you really get this stuff ingrained in your thinking, in your instincts, in your intuition? You play with it. I hope after this class, you will play with this notebook and experiment on your own time. All I'm saying is we knew that we created y train was based on x squared, in fact, 2x squared. And notice we got the coefficient we expected now too. Before it used 3 to compensate, to reduce that error as much as possible. But by playing with this and experimenting with, well, if I have a function, y equals x squared, a plot of x versus y is only going to look linear if I plot x squared versus y. I hope that makes sense. And if it doesn't now, it will over time as you keep thinking about it and playing with it. I can't emphasize enough. You will learn better if you do more than just use the modules. If you play with them, if you experiment, if you look at questions you have by trying to do the math by hand, derive the math. It's hard, but you can learn to do it. Code it up from scratch yourself. You don't have to do that when you're first learning, but over time, as you want to understand things deeper and deeper, learn to experiment more and more with deriving the math, with coding it up yourself, with running a bunch of experiments with these modules. Okay, so now oftentimes with multivariate models, there's a lot of possible engineered features. Now, again, what is our engineered feature? It's x squared, the feature value squared. Well, if we have multivariate models, we could have x1 squared plus x1, x2, excuse me, x1 times x2. Let me type this. I'm going to put it in here.
I think we have a question from Karim. Karim is asking a very pertinent question.
Yeah, I will look at it, but let me finish this.
Okay.
Say we have x1 and x2. Now this is simple. And by the way, I've had this case before where it got really complicated. Engineered features shoot, sorry, typing too fast. Could be. Now, in addition to x1 and x2, engineered features could be x1 squared, x2 squared, and x1 times x2. But that's for second order. We could go to higher orders and the number of possibilities goes higher. Have I ever encountered this? Yes. And it was on a very challenging but very fun problem that I had to solve in the past. So, but that still could include x1 and x2. Again, if we went to x cubed, we could have x1 cubed and x2 cubed, but then we'd also have x1 squared times x2, x1 times x2 squared. We could have, and then still have these lower orders also. But as you could guess, that's going to create a lot of extra features and we may not need all of them. Okay. Just visualizing, does this look overfitting? Oh, you mean right here? Is this overfitting? Is that what you're asking, Kareem? And you can come off mute if you want.
Yeah, just looking at it, does it look overfitting?
Not at all. This is perfect fitting. Overfitting would be if it started to jump between these points. And I could actually create a model, Kareem, that would make it jump between all these points rather than just pass through the happy middle of them. How could I do that? By adding too much feature engineering. Does that make sense?
That makes sense. Yep.
Okay, good, good. And I didn't take the time. Kareem, help me remember when we get to the Q&A, let's just go look up some good visuals about what overfitting and underfitting look like. By the way, up here, this was underfitting, and it would have been fun to include an overfitted example. Well, like I'm saying, because we can have build up a lot of extra engineered features, some of them may become unnecessary. And we need to reduce our features, both original and engineered features, down to the best set of features. Well, what are one of the ways that we end up with features we don't know? Well, first of all, let me show you about colinearity. And I'm going to just call this fake colinearity. This is forcing a type of fake colinearity. And you may be thinking, wow, you're taking the square root of x1 and you're claiming it's going to be collinear. That's correct. Pearson's is very powerful at detecting collinearity, even with that. Again, we're doing the same thing except one additional new thing. Notice I've done a horizontal column stack of all my feature variables plus y. And notice I've got x4 included in my feature set, but I'm saying my label data, my outputs do not depend on x4. Now I hope that's very interesting to you. I'm running that. Now I'm going to run this. Let's look at what's happening. First, I'm building a data frame because I love handling stuff inside a Pandas data frame. Pandas data frames, once you learn how to use them, they're very powerful, very fast. They're built on top of NumPy, so you know they're fast. And I'm going to do a correlation on the data frame. Now, please note, this is part of Pandas because I created a Pandas data frame, and that's what data frame is. And I'm doing a Pandas method of the data frame to correlate all the columns in that data frame. And then let's go ahead and improve this. I'm going to do, let's do 10 and 8, I think will work. And notice I'm using Seaborn too. Why? Seaborn's got some extra nice things for things like this heat map we're going to use. Oh, another pedagogical note, learning note, teaching note. In the beginning, I think it's great to go out and plagiarize all the code you can from the web. Please plagiarize this notebook to help you build your own tool set. But over time, you probably want to go look at the documentation for the seaborne heat map and understand more about how do I set my own version of these so that I know how to set the CMAP string and I know what I want to do for VMin and VMax. In fact, I probably could improve this too. But now, in fact, you can see I can because I never go below 0 with this. You can, but it's not happening. So it may be good to change this to 0. In fact, well, I won't do it now, so we won't get off track. But notice, oh wow, X1 and X4 are highly correlated. Now, maybe think so. Well, we don't like that. We want each of these features, X1 through X4, to be highly correlated to the label, but not to each other. And this is telling us, oh, X1 and X4 are strongly correlated. Well, imagine you're in a soccer match, football worldwide, and one guy leaves his position and starts playing the same position as one of his teammates. Is that a very good team? Well, what if there's 2 guys in the same position on the field and there's still someone in all the other positions? Some of the time that could work better, but other times it could get confusing. So overall, we know it's best to have one feature doing each job for the model. And right now we have 2 features trying to cover the same area. Now we know as fake data prophets that X4 shouldn't be there, but it's still doing a good job. In fact, if we looked at the model accuracy, it would be quite good for this. So let's see what happens if we remove X4 versus removing X1, since they're both collinear. And look at this. It is notably better to remove X4 than to remove X1. But I want you to see something. This is with all of them present. And this one is slightly more accurate than this one. Well, did you know you could even just throw noise at the model training and it would do better than without that noise? It's not always the case, but it is frequently the case. And so what I'm trying to say is, don't get sucked into just doing what's most accurate in training. This is why we have the methods and the principles. The first type of features we want to get out of our data set are we don't want any collinearity. We want each feature to be doing one job, not 2 features doing the same job. So just wanted to show you that. Don't get caught up in that trap. But you might be thinking, and I hope you are, wow, but if I didn't know about that ahead of time, like we do now with the fake data, that's why we practice with the fake data, so you can see how these things react. Okay, now let's say that there's a feature that's just really not very important. And notice how I've handled that here. This feature is really adding no value to the predictions. Now, again, I'm creating the fake data this way. But here's one of my favorite tools to find those features that really are no better. What I'm trying to point out, this is less significant than the noise in the model. I hope y'all see that, because again, the noise is at this level. Look at how much smaller the influence of X4 is. So now I go to statsmodels.api, I alias it as SM, and then I also import stats. Yeah, why I did that. I may not need this line, okay? But from the stats models API, this OLS, ordinary least squares, I take my labels, I take my features, and I do a fit with that model. And I look at a summary. And this is great, by the way. Well, let's look at this. These are my p-values for each of the features. And notice that, well, yeah, it predicted it had a small effect, but its p-value is saying, you know, this isn't really much different than the average, is what a p-value is telling us. It's no different than the null hypothesis. The null hypothesis with all coefficients in a model is the same. It's saying that this feature is not important. And it's confirming that this one's not important. If I run a new set, I've gotten higher values, by the way, for p-value. Look how high it was that time based on the random noise. So we could go on and on. We're going to always find that it's not very surprising where all of these are saying, oh, this is much better than the average. You should reject the null hypothesis that all of these predictors are better than average. Well, that's great. But there's another method. You can, like what we did above here, where we tried removing one feature at a time. There's some other good methods that I know you can do now based on this notebook, and this would be a great thing for you to go try. And you could watch one of our old class lectures that shows you how to do this. Try one feature at a time. Just start with one at a time of the feature set. Train a model and see its accuracy. But you add the feature to the growing feature set that yields the best training accuracy. Then you repeat that, but now you keep that most important feature and you add a second feature one at a time from the remaining features to the feature set. And the one that increases the accuracy of the most, based on that, you keep that one as your second most important feature, and you keep repeating. And that is also a good way to find out which features are most important. If you approach something like, you know, a really good model accuracy, let's say it's 0.899, and the next one just barely bumps it up to 9.000. Was that feature very important? No, it's probably no better than the noise. So that would be the stopping point. When you see that the next most accuracy enhancing feature does very little, it's probably good to leave that one out for parsimony's sake. Parsimony is our fancy word to just say the most elegant model. Elegance is a spirit of saying it's not too much, it's just the right amount, and it's beautiful because it's just the right amount. Now, you do a similar technique by starting with all features and removing one at a time. You can remove the feature that had the least impact on the training accuracy, or you could remove the feature that has the biggest impact on training accuracy. I tend to like the latter one. In fact, I should add that one. Or the one that had the largest impact on training accuracy. Now notice I'm not creating a train test split. That's because I'm just looking at the effects of the features. I'm not actually trying to create predictions. I'm using the modeling, excuse me, to analyze the features, okay? Okay, now how to condition features for accurate reduction and excuse me, the features for accurate, I should change this just a little bit, feature reduction and feature engineering, just to be extra clear. Oops. So to do that, we need to scale the features. Now, there's a lot of scaling methods. You need to study your data carefully to determine which one is best for your data and your modeling needs. But sometimes it's best determined by trial and error. In other words, we're creating a pipeline of processes that we can automate. We get the input data, we run it through all these processes, and finally through the training of the models, and we evaluate. But we write our code, we write our pipeline in such a way that it's easy to change what methods we're using at each stage. And I'll describe that a little more as we go. Well, some of it we already did. You saw how down here in Crossfold, we had versions of all these models, and we looked at which one was best for Crossfold validation after we'd done some individual exploration. So I'm going to create some fake features again, but look what I'm doing now. On this uniform data, I'm going from 0 to 1, and then from 0 to 10, from 0 to 100, and 0 to 1,000. And then I stack all those features together and I put them in a data frame. Why? So I can use this wonderful method to the data frame class called describe. And describe gives me my feature, my variable count for each feature, my mean, and these are just like we'd expect. Close to 0.5, close to 5, close to 50, close to 500. The standard deviations, they're going up by an order of magnitude roughly each time, like we would expect. The min, all close to 0, like we'd expect. The percentiles, the quartiles, the 25th, the 50th, and the 75th, and then the max. And they're all close, just like we'd expect, close to 1, close to 10, close to 100, close to 1,000. Well, if I'm going to get the good results I got above and be able to compare, like right now, this one, there's because these are at different orders of magnitude, I can't use all the tools we looked at above as reliably. I can't look at feature importance the same way. Now the p-value, yeah, but trying to discern which one's most important to model accuracy, that can all be confused by these magnitudes. So we want to scale the data, and one method that's very popular, let's see, is standard scaling. So how do we do that? We get the mean and the standard deviation of the feature values, and then we subtract the mean from all of those feature values, and we divide each of those new values by the standard deviation. That creates a standard normal distribution for all of them. And so let's test that. We're importing the standard scaler from scikit-learn's pre-processing. We do a fit transform on these features, and look, oh wow, all of these are close to 0 for mean now. Still, we get a count of 1,000 every time. But look, the standard deviations are all 1, like we would hope. The mins are all close to 0. Excuse me, they're all negative. These are all, excuse me. The maxes are all roughly the same as the opposite sign of the mins. And then again, the means are near 0, like we would expect. So we've got this spread that we were looking for that's been standardized with a standard deviation of 1. Now, why isn't it going out to 3 standard? This is a bonus question, and I'm going to let people come off mute who might be brave enough to, and it's okay if you answer wrong. I would love some attempts, but notice that here's our standard deviation of 1. Why aren't we seeing something more like 3 or 4 and sorry, for the minimum, why aren't we seeing a -3 or 4? Can anyone help me answer that? Okay, I'm going to give it away. If I had created random normal
I think
data,
Karim wanted to give it an attempt.
go on ahead, Karen. I think I already
So,
gave it away though.
yeah, so I think it's because we're looking at the mean and there are some outliers in the data. So if
No,
we were
not
using,
at all. Actually,
okay,
no. It's because we did random uniform data. Had we done random normal, then, and we would have been putting in values for mean and standard deviation here, then we would get something that went out to, for the min, about 3 standard deviations to the left and about 3 standard deviations to the right. But we did this on uniform data, and that's okay. Now, for that same reason, you see that the distribution of your feature variables are uniform. You might want, and they're all positive, it might be better to use min-max scaling. And so we look again, yep, we're back. We're just using our original data frame that had the different orders of magnitude. But now we apply min-max scalar, and I aliased it as capital MM. I instantiate it and I do a fit transform. And then I create my DFMM data frame and I describe it after I've done this. And look, all of my mins are exactly 0. All of my maxes are exactly 1, and I've got all sorts of values in between. So if you notice that your data is uniformly distributed, it's probably best to use min-max. But to use these powerful comparisons between feature weights, I would encourage you to try to apply the same type of scaling to all features. But I wouldn't say it's absolutely necessary. I just say it's strongly encouraged. Now, I want to point something out. Notice every class for scaling has fit, transform, and fit transform. Let's be very careful. The reason I do fit transform is just because I'm demonstrating things. If this were training data and we were doing this in a model pipeline, model where we're going to make predictions, I would do only the fit transform on X train. But then I would only do transform on X test. I want to use the same scaling that I got from X train on X test. If you don't do that, then you're not keeping things consistent. It would be like saying, I'm using a different pipeline now. You want to use a consistent pipeline. Now, if you find that a better scaling thing works better, you change all of that on your training data. And then as new data comes in, you're using those transformations as they were trained on the new data. You're not finding a new fit for scaling on that new data. I hope that makes sense. Now, there's another thing we have to do to condition the features properly. Some of the features have text. And let's remember, all machine learning problems are, typo, are math problems. So because of that, we must have numbers. And there are many text to number methods in the data sciences, and some of the methods used in transformers are very clever and very elegant, and other areas too. But the two most common and basic for basic machine learning are one-hot encoding and ordinal encoding. Because it's a little easier, let's look at ordinal encoding first. Now, I'm leaving it as an exercise to you to figure out how to use scikit-learn to do ordinal encoding. But I personally like to do ordinal encoding while I'm still in a pandas data frame. And as you've seen, it's pretty easy to create a pandas data frame. So here I create an empty one because I wanted to show you how to do this too. And then I say dfx1 equals my x1 from above, but now I'm reshaping it to just a row because pandas can handle this. And then I say, well, I want to know the number of rows, and then I'm going to make data frame x2 column just my x2 reshaped to a single dimension array. Again, they were the number of rows by one column, but this is code. So we have to do this to make the code happy. Now I create what are called ordinal values, meaning it's clear from the words that it's a scale of quality of some kind and that we could put them in an order. So I've got worst, poor, fair, good, pretty good, very good, best. And I'm doing some tricks here. I'm going to create a new series called quality, for series is a column in a data frame. Series is a column in a data frame. And so I'm creating my third column, and I'm just saying it's a series. But see, I'm assigning this series to this data frame. So it'll be the data frame's third column. I'm saying make a series out of a random choice from this quality list, but do that the number of rows times. So for the number of rows, do it that many times. In other words, for that many times, pull a random choice from this quality list and create this series with it. And boom. So I've got my x1, just like before. I've got my x2. And I've got these text values. Well, so how do I create, hang on, I'm just double checking some stuff. Okay, my ordinals, I'm just saying my ordinal numbers, that is, it's a list. And I'm using this Python range command to go from 1 to 8, or really 1 to 7, because it's going to stop short of 8. And I turn that into a list because this is what's called an iterable. It doesn't persist, but by declaring it to be a list, it'll stick around. Then I use this second trick. And when I do an underscore capital D, that's my shorthand for a dictionary. I'm going to create a dictionary of two lists zipped together. The quality list from above right here. Let me scroll up just a little bit. The quality list here and the ordinals. And so every time, if you say, well, what's worst assigned? Worst is assigned 1. Well, what's poor assigned? Poor is assigned 2. So we're going to actually, you can see I've already done it. Worst is 1, poor is 2. This is what the dictionary looks like. And I'll just rerun it. But what are we doing? We used this data frame replace method in the data frame class of pandas to say, use this dictionary to replace every time you see worst with 1, every time you see poor with 2. And you can see here, we started with poor, we replaced it with 2. Very good is a level 6. Pretty good is 5, best is 5, fair is 3. Yep, it's all working. So this is the slick way to keep track of things in pandas and do ordinal encoding. Well, in the same way, there is a one-hot encoding class in scikit-learn. And I think it's great. By the way, I think the ordinal encoding class of scikit-learn is great. I just like to use pandas because pandas keeps things very clean and it's fast. So I created this class, and I'm going to let you study it on your own time, to do one-hot encoding inside of pandas data frame. So I'm gonna define this class, and notice I've already gone ahead and created this note here, and then I create an empty pandas data frame. I add x1 to it again, I get the number just like we did above. I create X2. Now I have a color list and I create a pandas column in that, excuse me, I create a column in that same data frame and I create a series to assign to it. And it's that same thing. Choose a color from the color list for number of row times. And in case you weren't aware, when you're in a notebook, if you just declare a variable as the last line, it will print it out. But if you do anything above before that, you need to force the view of it. So I'll rerun this so you can see. And yep, I've got just my fake data set with these color words. But in this case, we're not saying red is better than blue is better than green. We're just not doing that. But you can see I've got blue present. Now I need a column for green, red, and blue, or do I? Well, now I'm going to run that class that you can study later. Oh, wow. Where did green go? Well, let me show you something. If red is 0 and blue is 0, what is green? What I'm getting at is when these are both 0, it's perfectly understood even by the model training. Oh, that's green. But when one of these is 1, nope, that's blue, that's red, that's green. That's green also. That's green also, etc. Why do we do that? It's kind of a type of colinearity. Everything's completely defined this way. If I add that extra one, if I'm using just the right model, it won't care. But it's cleaner. We get better mathematics in the training on a lot of models if we don't include what we call the dummy variable. So when you're one hot encoding, it's the number of categories you're encoding minus 1. So you can see we're only doing binary when we do one hot encoding. That's why it's called one hot encoding. If it's 1, that means it's that one. If it's 1 here, that means it's the blue. If they're both 0, it means it's the green. I think I beat that to death. Okay. How to clean dirty data. Very carefully. That's not very helpful, is it? Well, if you keep learning Python and NumPy and Pandas very well, and you get very good at Google searching for things that you need and understanding Stack Overflow answers and Geeks answers and other great posts from blogs out there in the wild, you're going to do fine. There's no class that can possibly cover all data cleaning methods. But if you guys want to have a 4th session, I actually thought when Guy filled in last week that I would still have another session after this. So Hugo's going to survey y'all to find out, do we want to go one more week and cover cleaning data? I recommend we do. But again, if you do what I'm saying here, you will do fine in the long run. Okay, I'm eager to take your questions now. And while I'm waiting, I'm going to go look up something for y'all.
All right, I think this will be the right time to take Karim's question first on whether there are other modules that could be used to do machine learning that are as efficient as scikit-learn.
Yes. Okay. I'm assuming y'all have all heard of TensorFlow and PyTorch. So those are other modules, libraries, that will do a great job, but they don't do everything that scikit-learn does, and they don't all do it the same way. And then notice here, let's go look here. XGBoost, when we looked at that, if you look at AdaBoost, for example, look here, scikit-learn .ensemble import AdaBoost regressor. But when I import XGBoost, import XGBoost, what does that mean? That means this is not part of scikit-learn, but it's very important. Why doesn't scikit-learn include it? Because it was made by the XGBoost group. You go to the XGBoost site, there's a great Geeks for Geeks example. I personally find their site very confusing, at least for what we're looking for. So there are examples of these things outside of scikit-learn that, yes, we use them. But then there's other languages like R, and they have their own libraries and modules. And there's Julia. And then there are small movements out there in the wild where there's companies that have their own C++ libraries, and they're companies and they create their own libraries for special use that they use out in the wild with companies that they serve. Now, I'm going to trying to find a graphic for y'all. Oh, I just want something simple here. Okay. Then I'll take Nima's question before I go to this graphic I'm looking for. Let's see, maybe. What? That is very frustrating. There we go. Okay. Y'all seen that? Here we go. I'm bringing this into view for a moment. This model is properly fit. It's not overfit, but you can see how here's a true function, they're calling it. But here's a model that has too many features, maybe too much feature engineering, and it's beginning to overfit, especially down here. That would be an example of overfitting. You've seen my example, that this is similar to my example of underfitting, where they're trying to use a linear feature to fit a non-linear label. What else they have here? This is beautiful graphic for cross validation, by the way. See if there's any more. Yeah, if you do a search on overfitting and underfitting, you'll find a lot of interesting things, but there have been some really good graphics in LinkedIn posts to show over and underfitting. Okay, metrics. So in regression models, R squared is the king, and it's very well understood. Basically, it's looking at the squared residuals of the lot to the lot. So the predictions to the model, but it's dividing that by the average. And as you can imagine, and then, excuse me, you take that as a function. So it's the residuals notice this was one example where we initially got a negative R squared. I wanted you to know it's possible. If you were here last week, you saw that it was. And we just had to change the hyperparameters in that case. But getting back to what we're discussing. R squared is so good because it's first a ratio of the residual of the predictions minus the actual output values, and then those are squared each. So it's like, oh, well, when X is this, what is Y predicted minus Y actual, and then square that. And then we sum up all those square values, We divide that by y average, and we subtract that fraction from 1. So if the model's perfect and there's very little residual error between the prediction and the actual values, R squared will approach 1 for really good models. By the way, these are insanely good accuracies we've been working with on most of what we're doing, because we're using fake data so we can really see things and understand things. But model accuracy of 0.8, 0.85, 0.9, those are really good, by the way. You pray for accuracy that good. But are there others? Well, we look at error too, and that's also a great indication. So let me go down to where we were at the feature engineering stage and look at those metrics again. So mean squared error. This is just saying I sum up all those errors of y predicted minus y actual, square that and do that for each of the predictions. And I should go down here, look at this one. And so when I sum up all those, I then take the mean or the average. Now, the root mean squared. Well, what this is meaning is after I get the mean squared error, I'm going to take the square root of all of that. Then there's the absolute error, meaning I get each of those errors and I just take the absolute value and then I average them. And then there's the absolute error, but we look for the median instead of the mean. Again, the median, if you sort all your values, my little dog wants that. After you sort all the values, you look for the one that's in the middle. And if you have an even number, you look for the middle two and take the average of those two, unless it's the same value, two values in the middle of an evenly numbered set, then you can just take it. And then R squared is like I described. It's 1 minus the square errors over the mean of the data set. And yes, the average. And we can double check that, but I'm pretty sure that's right. I might be off a little bit. It's the spirit of it that makes most importance. Good questions. Nima, did that help, Nima? Just you can answer in the chat or come off mute. And are there other questions?
Okay, so while we wait for some other questions, I'm going to launch 2 polls actually, because we need you to help us direct our tech chat with Thom. We want to make this very big, and we want to ensure that it helps a lot of people in the data science community. So we're going to launch 2 polls right now. The first is this. I'm just going to launch it on your screen. So please just look at them. Look at the question. The first one is, would you want us to have a further session with Thom, like data cleaning, stuff like that? Would you want us to have a further session beginning from next Saturday? And feel free to answer. Yes,
Modupi, that message you just sent, it only went to me. You need to make sure it's to everyone. But Modupi says, hi, everyone. It's nice being here. And we're very glad you're here. Oh, excellent. And please, guys, I think those of you that know our family, you already know this, but let me tell you something, and I'm just going to beg you to believe me. I want to be the best teacher I possibly can be. I've told Hugo that by the time he gets to my age, he's going to be a much better mentor than me. And I actually believe that. Now I'm asking him to believe it, but our family's trying to grow more together. And that's why I believe Hugo will be a better mentor than me someday. But you will help us the most when you say, okay, Ruin, really glad you came. Let us know where you're still confused. I'm not gonna take it like, oh, I didn't do a good job there. Guys, this is hard stuff. And we're talking about where the rubber meets the road. We're talking about how to do basic machine learning. And we've done very simple things here so far, but like Hugo's saying, we want to make this better. So I think it's going to be a teamwork effort between what you suggest and what I know. We'll meet in the middle to get you up to speed as fast as possible. So yes, we want to do more sessions, but also let us know where this was great. That helps too. Where you got completely lost, that helps us even more. We're not going to take it personally. We're going to take it like, okay, how can we make that better together, please? And you go on. I just wanted to add that.
Right. Thank you very much. That so like we explained. Okay, let me just launch the second poll and then we'll talk more about that. So I think I can end this one right now. And let me launch the second one. Just a second. Okay, so you will see another one on your screen asking you which of the following would you want us to have next from here? So would you want statistics for machine learning, math for machine learning, training on specific libraries, maybe scikit-learn, pandas, numpy, tensorflow, keras, or you want to learn some techniques like PCA, pre-processing, and all those? Which one would you want next?
Training on specific libraries. You know, and I'm not criticizing y'all, but Hugo, let's put a poll there. How many people want to make sure we cover all of these? What I'm wondering is maybe this is about which one they want to do first.
First, yes, first.
Yeah. Do you, I'd like to know in the chat, who would like to see us cover all of these?
Okay, so yeah, Nima.
Good, Nima. Great. Right answer. In other words, you know what, guys, I would have suggested, like what you're saying. Yes, we want to cover the math and statistics, but I agree with y'all. I think it's going to come out. I want to know how to use the tools as soon as possible. I kind of agree with that, because what you will be learning the math and the statistics by learning to use the tools. I think what we're asking about the math and the statistics is understanding the math and statistics at a level where you could code this from scratch. And so I'm guessing you guys would even like to get to the level of coding from scratch. But think of it this way. If I were encouraging you guys what order to learn it in, I'd say learn the tools first, because then they can help you experiment as you learn the math and statistics. Does that make sense? Hugo, someone drew on my screen.
Absolutely.
Is that Nathan doing that?
No, it's not Nathan. Okay, so I think we'll have the results in already. Should we have another training next week? Yes, overwhelming yes. Everyone says yes. So we're going to have another session next week. And like that says, I think the right order, especially the order in which I learned it, is understand the libraries, then the techniques, then the statistics and the math. That was how I learned. I'm still taking lessons on the statistics and the math. It's a never-ending journey, really, right? But so if you ask me, I think next week that probably should do the libraries. Maybe we should take scikit-learn, take those your favorite libraries. You do a lot with fit transform. We want to know what about it, how it works, the things that it does.
What if we, Hugo, do you think we should repeat my NumPy lesson, maybe?
Oh, we can even start from NumPy. We can start from NumPy. That's a good place to start. Very, very great start. Very great.
Now also, should we go through some of the more common and most encountered dirty data and how to clean it? I know that's not very sexy.
That would
I
also
want
be
y'all to
great.
know, if you're, let me put it this way. Let's say you're trying to get your first role and you're hoping it will be a data science role, and you're trying to differentiate yourself from other, how should I say, you're trying to differentiate yourself from other candidates. And in a cover letter, you just say, I want you to know, I know the new data scientists typically get stuck with the data cleansing and the data conditioning. I love that stuff. I think it's super important, and I would be thrilled to do that in my first role. They're going to go, oh, nice. And if you make sure no, don't open that one. If you make sure you're getting really good at that stuff, that will make sure that people know you love to clean data and format it correctly for data storytelling and for machine learning. In fact, I'm interviewing a lot right now, and when you mind doing, I expect to do that. I think it's the most important thing we do. They love hearing that, by the way, even from someone at my level. So please don't hesitate to make it known that you are a clean, well-formatted data freak. They will love that.
Okay, great. So I don't have any questions in my private message inbox. So I'm just going to ask if you have any that.
Oh, and she's Modupi. I hope I'm saying your name correct, Modupi. You keep sending direct messages to me. I don't think you mean to, but that's what's happening. I don't know if Modupi is a guy or a girl name. I apologize. Please, can we choose more than 2 trainings to attend? I'm always interested in attending technique of machine learning. Yes, and Hugo will let you know about our recorded lectures for the class that the machine learning class that Guy and I are wrapping up. It's based on the book we're writing. And you can watch those lectures and ask Hugo or I or Guy questions in our pipeline class chat or this tech chat on our Slack. Please go through those old lectures and, don't be afraid to challenge us too. Like, oh, I wished you'd have said more on this, or I didn't like the way you explained that. We don't take that personally. As long as you mean it constructively, we take it constructively. So, but watch all those lectures. Hugo, do you have a link to the time that either Guy and I or me and Louis and Tina taught the overall machine learning pipeline?
I do have that.
You know that? Okay, make sure everyone here gets a link to one of those talks, because that's a big overview without math or code on this whole process I've walked you through.
All right. I'll do just that.
So with everyone's permission, we'll go through some fun, basic data cleansing exercises next week. And
right.
then we can, the week after that, we can go into a NumPy class. And then you guys are the boss. You say, oh, that was a good intro, and now we want to go to pandas, or, oh, that was a good intro, but we want to go deeper. Y'all will be the boss. And it might get to a point where I do real time. Like this lecture today, I'll stop sharing my screen, but this one that we did today, I prepared that. But we can do some real time stuff too, where I'm doing it on the fly, and you can watch, oh, Thom does a lot of trial and error coding too. Yes, I do. I mean, it did, at my skill level, did I do much trial and error? No, in fact, I was cutting and pasting from other stuff I knew that worked. And I would probably, keep a lot of resources open when we had that session. But I just want you to know that, yeah, I don't mind showing you my trial and error coding, and I might say, oh, let's go look some up. That way you can see the way I go about coding, the way I look things up, etc.
Okay, that would be great. That would be great. So I'm going to send a mail out with those links. I'm going to send a mail with the link to the recordings, the link to the notebooks, and also other videos that mentioned. And then I'm also going to send a mail for next week, just to notify everyone, especially those who registered but could not make it, that we are going to start with data cleaning next week. And then after that, we're going to NumPy. And NumPy is very important, I eventually discovered, because practically every machine learning library takes NumPy arrays as inputs. Scikit-learn, PyCaret, any of them, they all default to NumPy arrays. Now, I know some can accept pandas, but NumPy is like the de facto standard for machine learning libraries, and that's why it's key. It's key with learning. Yeah.
NumPy is to term coding. How do I say this? Running things in a terminal as pandas is to running things in a GUI. Not a great analogy, but it helps you. Pandas does some great things, additional things that NumPy can't do, but Pandas is definitely built on top of NumPy and a lot of other very powerful Python libraries and modules and classes. And then SciPy even more so. So both Pandas and SciPy and sklearn depend heavily on NumPy. That's why we like to be able to understand things in both. But you may have noticed where you might have thought, oh, I want to pass a NumPy array into here. It's okay to pass a pandas data frame into that same thing usually. What it's probably doing though is that class method in scikit-learn is saying, oh, this is a data frame. I'll have to get the values from it. And if you've seen me do operations getting just the NumPy array from a pandas data frame, you've probably seen that, oh, that was easy. And it is. It's easy to go back and forth between, when you go to pandas to NumPy, it's very easy. When you go from NumPy back to pandas, it's to a pandas data frame, it's not as easy, but it's not overly hard. You just have to do a little planning when you go back to pandas. Guys, I can take a break until we get to integrated mentoring, but I'm going to stay on here as long as you guys want to ask me questions. And it's okay if you want to, if you just need to leave, or you're planning to take a break before integrated mentoring, or you're not coming to integrated mentoring, you just got to leave, please. All's fine, but I'm going to wait a couple more minutes. If there's no more questions, we can close out. I hope this session was valuable. And please see my last message in the chat. I want everyone to always show as much or maybe more appreciation to Hugo, because he is probably the biggest giver in our family, our integrated family. So if it weren't for him, we wouldn't be doing these sessions. And we've been looking for a way to make tech time chat more valuable, and I think he's nailed it.
That
if you don't, no one be shy about hanging up if they want to. And then Nima's saying, yay, yeah, Tom, great help. Thank you. I will join the mentoring session. Good. Yes. Everyone make sure. The only way you can make me mad today is by not thanking Hugo, either personally or publicly. So make sure you thank Hugo. He does a lot for the family. And I would imagine his Power BI classes are to die for. I studied Power BI. I feel like I could use it if I needed to, but I don't use it in my kind of work. But if I went to a role where I was doing a lot of that kind of work, I would absolutely. I know I've never learned Tableau. I've only learned Power BI. And if I didn't have access to Power BI, I might be tempted to try Google Data Studio, but I don't think it's as feature rich yet as Power BI and Tableau. But those are really great data storytelling tools if you're not feeling very up to speed with Python. And even if you are a Python expert, you might still prefer to use one of those tools. So I guess what I'm trying to do is give a plug for Hugo's Power BI training also. Okay. And again, don't be afraid to just hang up. I'm just hanging around in case people have questions. Hugo, I think that's a clue that we can end the meeting. What do you think?
I say that's fine. That's fine.
All right, very good. Well, if you guys felt help, then I'm blessed. And if, again, please do not be shy about saying where you got confused. You can't imagine how much that would help us so that we know what we can work on to make more clear when we teach this stuff. All right. One last 10 seconds, and then I'm going to hang up. Unless there's a question, then I will hang around. All right. I'm going to sign off, guys. Take care.
Bye.
Bye, Hugo.
Bye then.